Hello. Hello, is it visible the slides?
Yes, ma'am.
Okay. Just a basic
Yes, ma'am.
information regarding the introduction of digital image processing here you can see in today's class. Just as might be you have completed the third and fourth and fifth units also, but still as a revision, now I'm concentrating on these particular topics only. Now let us see how why it is not moving. Okay. Uh, In this course, basically the introduction of digital image processing as well as fundamentals and transforms, enhancements in spatial domain, enhancements in frequency domain, restoration, segmentation, morphological processing, compression. Total, these are the topics of the units in your digital image processing and simple image formation model. I'll go for, yeah, simple image formation model. If you observe how it is, yeah, just see here. So image is denoted by two-dimensional functions f of xy and value of amplitude f at xy spatial coordinates, which is a positive scalar quantity. And image generated by a physical process, intensity values are proportional to the energy radiated by the physical source. This already just completed, but as an introduction part, the intensity of any pixel value, it depends on particular range that depends on radiated by a physical source, that energy radiated by a physical source. That's the reason f of xy ranges in between 0 to infinity. Okay, then f of xy may be characterized by the two components: the amount of source illumination instant on the scene and amount of reflected
Sound like
energy,
sound like
yeah, amount of illumination reflected by the objects from the scene. So this is called illumination and reflectance. So f of xy is equals to I of xy, r of xy. That's a multiplication of I of xy and r of xy. So I of xy ranges from 0 to infinity. That means maximum source of illumination is infinity and minimum source of illumination is considered as 0. And reflectance, a minimum is 0 and the maximum reflectance is 1. So these are the ranges of illumination as well as reflectance. So reflectance value, if it is 0 means total absorption occurs on objects. If it is 1 means total reflectance occurs from the objects. That's the meaning. Now, so typical ranges of this I of xy visible light, just if you observe some natural sources as a sun here, on a clear day 90,000 lumens per meter square down to 10,000 lumens per meter square on a cloudy day. So these are the minimum and maximum ranges of sun in terms of lumens per meter square, that illumination of light from this sun. In case of moonlight, that is a full moon on a clear evenings, approximately zero point 0.1 lumens per meter square. It's very, very small as compared to any cloudy day environment of sunlight also. So typical illumination level in a commercial office, approximately 1000 lumens per meter square. These are some information regarding the illuminance, and these are some values regarding reflectance based on the material or objects. Point not one reflectance from the velvet, black velvet glass or black velvet colors. 0.65 for stainless steel, zero point 0.8 for white walls, and 0.9 for silver plated. And from snow, 0.93 maximum reflectance from snow, you'll get it. Then monochrome images have your ranges means intensities L minima to L maxima, and L minima is equals to the multiplication of illumination and reflectance of minimas, and L maxima is equals to similarly multiplication of illumination and reflectance of maximas. Typical limits for indoor values in the absence of additional illumination, that is L minima is approximately 10, L maxima is equals to 1000. That is in case of indoor illuminations, is called the grayscale or intensity scale. L minima, L maxima, that is called actually the grayscale. So in common practice, in general, we are denoting that as 0 to L minus 1, where L is equals to 0, that indicates it's a black, L minus 1 is a white. This block diagram also might be come across in the class. So image processing sequence, how we are capturing the image. This is an actually the three-dimensional world, what we are observing in the nature, that image, and capturing through the cam. And through after capturing through the cam, then digital image processing is taking place. That digital image processing means a particular system focuses on this water drop, and water drop is actually we are focusing on improving the quality, then the processed image appears like this. Based on our own application, we are going to process the part or full image based on application only. Accordingly, we have the results at its output. So the basic concepts in fundamentals like sampling and quantization. After capturing sampling and quantization, the next processing steps. So basic concepts in sampling and quantization. What's meant by the sampling and what's meant by the quantization? Digitizing the coordinate values like x, y are called sampling. Digitizing the amplitude values like f amplitude, that's called quantization. Now, if you observe this particular diagram, already this diagram, if you are present in that classes, it's a clear. This is an actually the background, and this is an actually the foreground of an image. This foreground is appears to be a grayscale, or we can consider as a black, but it's not pure black. It's having grayscale. The light is focusing at the center of the objects. This is actually the original image given. Suppose how we are going to do the sampling of this particular image as well as the quantization means. Let us take as an example of draw a line over it and consider for this particular line you have to do the sampling as well as quantization. The same thing you can continue for total image by row wise as well as column wise. That is row wise you have to complete. If you consider AB line, then see this background is a white and foreground is a grayscale. That's why here from this particular edge to the border of this object it's a white. That's the reason it's showing actually the maximum intensity of from edge to the level of boundary of this particular object. Then while entering into this particular object, this seems to be actually the black, but as compared to this portion, this is a pure black. That's the reason the level of gray level showing very low level, which seems to be actually the black. Then while moving this line at the center of this object, because of this light fall on this particular object, it appears to be somewhat brighten as compared to at its edges. That's the reason the intensity here increases from black to the gray level, and after reaching to this point, then again it decreases. Again, it reaches to the same black. That's why this type of reducing of the grayscale from again grayscale to the black it's showing. After coming to this point, then immediately at its edge of the object, it changes, abrupt changes occurs from black to the white. That's why this abrupt change you can observe from black to the white again this level. This is an actually figure shows a scan line from A to B in the continuous image used to illustrate the concepts of sampling and quantization. With this example only have to write the sampling and quantization. Now, this diagram, so this is actually after extracting this, then you do the sampling over it and as well as quantization. If you do the sampling here, sampling just, what's meant by the sampling? Digitizing of spatial coordinates, like digitizing the coordinate values is a sampling. That's why digitizing the each and every coordinate, these are the actually the small circles represents here, squares, not circles, small squares representing digitizing the spatial locations. And quantizing, I mean, what is meant by actually the quantization? Digitizing the amplitude values. Based on its amplitudes, if you have digitized, these are actually the quantization. Based on its amplitudes, we are giving these values to this particular pixel locations. This is called quantization, and this one is called actually sampling. With this particular explanation, I have to explain sampling and quantization. After completion of the sampling and quantization, this is the digital scan line shows this type of location and its amplitudes with the sampling and quantized results. So this is the basic introduction of digital image processing, sampling and quantization. How we can do this sampling by the sensor or arrangements means we have single sensing element as well as the sensing strip and sensing array. Single sensing element combined with the motion and sensing strip and sensing array. Extending of single element we will call it as in a horizontal manner a sensing strip. Extending of a single element or sensing strip in a row wise, that we'll call it as sensing array. That means just here given a spatial sampling based on number of individual mechanical increments. The number of sensors in the strip establishes the sampling limitations in one image direction, in the other same value taken in practice. That is, in a strip means the same elements if you have repeated for sensing of or objects, or sensing of capturing of images, that particular I mean sensing device will call it as a strip. And array wise, if you have arranged these particular sensing elements, the number of sensors in the array establishes the limits of sampling in both the directions, that is horizontal as well as vertical. That will call it as sensing array. This is an example here. If you observe the same example of background with the white and foreground with the black, and after digitizing continuous image projected on to a censored array, then resultant of image with the sampling and quantization it shows in such a way. So sampling and quantization, these are the values, intensity values given based on this particular locations. These are called actually the quantized values, defining even though it's not fulfilled, but you have considered this particular total black, I mean total block here. That is actually here sampling mechanism we are applying, and based on intensity, the total block we are giving same intensity. That is called actually the quantization. So after sampling and quantization, this is an actually input and this one is an output. So quality of this digital image is determined to a large degree by the number of samples and discrete intensity levels used in sampling and quantization. Are you following? Hello?
Yes, ma'am.
Okay. Still, if you have any doubts, you can ask me. Okay. But unmute your microphone and then ask. Clear, ma? Okay. Now, representing of digital image already we come across in two-dimensional array wise f of xy we are representing that image consists of m rows and n columns. That is location, spatial locations of x comma y. X is equals to 0 to m minus 1 and y is equals to 0 to n minus 1. M rows, n columns. So a section of real plane spanned by the coordinates of spatial coordinates xy. Xy's are spatial variables or spatial coordinate. This diagram also just we already discussed, but how you are representing this digital image and how you are giving the values to the locations of the pixels based on its a grayscale or gray level values. Here image plotted in this way, but while observing this image as well as the two-dimensional image, and this is an actually three-dimensional view, and this is the two-dimensional image. But here the intensity values given on this particular three-dimensional view to the two-dimensional view, there is no relation lies in between these two. But better to consider this image and how you are representing the values for this image only you can observe. This is a black, totally a black portion at its boundaries, and in between you have a gray, and at the center a D alphabet is represented. So in general, we already come across in the gray scale, maximum value is a 1. Suppose if you have considered the normalized values, minimum is 0 for the black and maximum is 1 for the white. So we are representing 1 for the white and 0 for the black. Black means this is totally 0. And 1 means for the D. Then gray levels lies in between means if you have considered it is a 0.5 which is exactly center of in between the white and black, then you have given 0.5 here. In this way, just we are representing the different gray levels present in an image. Yeah, any doubt? Okay. So let us see. 1 minute. Just mute it. The digitization process requires decisions on the values of M, N, and L. A total digitization process based on the I mean, size of an image as well as number of discrete intensity levels of an image. Number of discrete intensity levels depends on what? I'm asking you a question. Number of discrete intensity levels depends on what we are categorizing. Hello, any one of you please respond. Astita, Amma, Astita. Hello, how many of you are present? 20 members only. Yeah, just now have completed MPMC class, is it? And now let us see here. Then, so no theoretical restrictions on M and N other than M is greater than 0, N is greater than 0. That's it. So due to storage and hardware, typically L is equals to 2 power K. L is equals to 2 power K. These are number of discrete intensity levels present in animes. K is a number of bits per pixel. So assume that discrete levels are equally spaces and integers are in the 0 to L minus 1 range. So K is number of bits per pixel. Based on number of bits per pixel, we are having number of intensity levels in an images. Okay. So dynamic range and of course saturation, contrast, dynamic range and low dynamic, high dynamic ranges and low dynamic ranges. Like these are used for representing of digital images. Dynamic range means the ratio of maximum measurable intensity to a minimum detectable intensity level in the system. We'll call it as dynamic range. Then contrast, of course, difference in intensity between the highest and the lowest intensity levels in an image, we'll call it as contrast. High dynamic range, high contrast expected. For low dynamic ranges, dull, washed out gray looks it gives for low dynamic ranges of images. This is an example we can observe. So here saturation, this particular spreading off or blurring of a particular region, we'll call it actually saturation of that color. These are saturated colors. Okay, this particular thing you can call it as a granular noise, or simply at this particular stage it's a noise only. This is the noise and this one is a saturated color. Like this, just we are observing based on the shades and based on intensities a different values of the pixels it's having, that representing a digital image. It depends on gray level intensities changes from point to the point based on its saturation, and based on noise it's having its own variations in its intensity values. Then the number of bits how we can calculate for storing of any input images or any images means that is b is equals to m into n into k. M number of rows, n number of columns, k number of bits per pixel. So b is equals to number of bits required to store an image means b is equals to, if I have consider squared image as m is equals to n, then b is equals to n square into k. So that image 2K intensity levels, if it's having means K or number of bits per pixel, I already told you. If K is equals to 8 bits means you can multiply M into N into 8. Okay, that is the actual number of bits required for storing of an image. You can calculate based on its size and based on number of bits per pixel in an image. These are just a calculations based on number of number of rows and number of columns. If you consider as equal, that is m is equals to n as a squared image, here given n value, that is 32, 64, 128 like this, and k values ranges from 1 to 8. That is sorry, l is equals to 2 means k value is equals to 1. So 2 power 1 is equals to 2. In this way, just given the values here, and based on this n value and k values, how you are going to calculate number of bits required to store an image. So m into n, that is m into n means what is actually here, m into n into k. If k is equals to 1 means number of L is equals to actually have 2. If k is equals to 1, then L is equals to 2. If k is equals to 1 means n 32 into 32 into 1. So 32 into 32 is 1024 into 1, so 1024. So now 32 into 32 into 2, this one. Like number of bits increases means here actually this number indicates a bits, 1, 2, 3, 4, 8 bits. So with the number of bits increases, automatically the number of storage bits also increases. Here size of the image increases, instead of 32 by 32, 64 by 64 into 1, 64 by 64 into 2, like this given tabular column based on number of rows and number of columns and number of bits required to represent a pixel in an image, we can calculate overall bits required to represent an image. Okay, if with 8192 size of an image, 8192 by 8192 into 8 bits. If it's having total number of bits required to represent an image is this figure. Okay, and then so these are actually spatial in resolution and intensity resolution. Do you want any clarification regarding the spatial and intensity resolutions again? Excuse me. Hello, Amma. Hello, please unmute your microphones. At least one or two members can interact instead of minimizing the noise. See, what for we are conducting these revision classes. Still, if you have any doubts, we are in a position to clarify. And there is no any ambiguity while going for the exams or before going to the exams. That's the reason we are conducting this type of revision classes. Is it clear? Hello, ma. Okay. Hello. మేల్కొన్నారా నిద్రపోతున్నారా? Okay. Sorry. I'm continuing now. Let us see. Spatial resolution and intensity resolutions here, if you observe, already just if you have any doubts, please, unmute your microphone and ask a doubt. So, spatial resolution measures the smallest discernible details in an image. The qualitatively and most common measures line pace per unit distance or dots. In general, we can measures in terms of this. That is dots per unit. Dots per unit, if you have represented on images, that shows an actually how you are going to give the importance for improving the qualitative quality of that particular images. That is in distance, dots per unit means that related to the distance measure on particular images. In general, for printing media or publishing industries, they will consider these particular distances. The distance measures or dots per inch. This DPI means dots per inch. That is according to the US standards, dots per inch. In case of newspapers, 75 dots per inch they can use for printing. For magazines, 133 dots per inch. For glossy brochures, 175 dots per inch. For digital image processing books, 2400 dots per inch. That's the reason quality of the images appears in this Gunjal's textbook. It's very clear as compared to any other textbook images. So key point to be meaningful here, measures of spatial resolution must be stated with respect to spatial units. So dots per inch or dots per unit, if you are representing the number of dots per unit, that is actually the spatial resolution. And if you go for intensity resolution, that is smallest discernible change in intensity level. That is number of bits per pixel if it is varying, that shows intensity resolution. Most common bits per pixel, 8 bits. Then if you have extended the number of bits, is it 16 or 24 or 32 bits? For high definition TVs nowadays we are using 32 bits per pixel, but 8 bits to 16 bits the quality gets improved. From 16 to 24 still it improves the better quality, but 24 bits means it's a true colored image. But high definition TVs still there is a chance to have improving the quality of an image by improving the number of bits per pixel. So these are actually this one is called intensity resolution, and increasing number of dots per inch we'll call it as spatial resolution. Is it clear? Is it clear? Okay. Here you can observe effect of that particular sampling with particular examples. The original image size is 3692 to 2812 pixels m by n. So 72 dots per inch. If you have considered for the spatial resolution, smaller images zoomed back to the original size. This one is first a typical effect reducing spatial resolution image 1000 1250 dots per inch diagram, this one. And this one is 300 dots per inch, and this one is 150 dots per inch, and this one is 72 dots per inch. So 72 dots per inch, if you have extended zoomed out, then how it appears. just here you can observe definitely some degrading the quality of an image with less number of dots per inch as compared to this and this. From here to here, if you observe, there is a chance to observing some a deterioration of edges because of reducing number of bits from 300 to 150 dots per inch. So 72 dots per inch, it's a clearly specifying the degrading the edges of or boundaries of this particular object. This is actually the spatial resolution example. And here you can observe 256 gray levels. I mean, size of an image is 452 by 374. It consists of 256 gray levels, 8 bits per pixel. And this images displayed in 128, 64, 32 gray levels. So 256 level is this one. I mean 8 bits per pixel it consists. Now coming to this one, it's a 128. That is here 8 bits and in this case 8 bits and this case 7 bits. 7 bits means 128. 128 bits per pixel and this one 64 bits per pixel. Sorry, 64 gray levels and this one is 32 gray levels. So 8 bits, 7 bits, this one 6 bits, 5 bits. But there is no much difference we are observing in these four types of images. But coming to this one, this is 16 gray levels and this one 8 gray levels. This is 4 gray levels. This one is 2 gray levels. That is number of bits is again reducing here. In this case, number of bits are 4. I mean 2 power 4 is 16. 2 power 3, 8. 2 power 2, 4. 2 power 1, 2. So 2 gray levels here appears. 2 gray levels means one is black and the one is white. So with this, we are observing how it is degrading the quality with reducing the number of bits. Is it clear? Hello? Hello?
Yes, ma'am.
Okay, done. Okay, these are effects of sampling and quantization you can observe. Isopreference curves, there is a chance to have question on isopreference curves. That's the reason I'm showing this one. This is a low level detailed image. Okay, this is low level detailed image and this one is medium level detailed image and this one is high level or large amount of detailed image. Based on this particular content appears in these images, I have named it as a low level, medium level and high level. So in these three images, if you observe how it is actually sampling and quantization taking place means this one is, more information is available in the third and this one is medium information. It's very less information in it. If you go for that experiment to study the effects on image quality, set these three types of images generated by varying n spatial resolution and k intensity resolutions independently. These three images, if you have considered and do some experiments over it by varying of spatial resolution as well as intensity resolution, how it shows the results on varying of spatial and intensity resolutions. Let us observe in this case. Observer asked to rank them according to their subjective quality. Okay, based on subjective quality, here they have evaluated this particular isopreference curves. These curves are called isopreference curves. So with varying of n and with varying of k. N means number of dots per inch or number of dots per units and k means number of bits per pixel. So while varying this number of bits as well as number of dots per inch on face means low level information image. On low level information image with varying of n here and k here. N from 32 to 256 we are varying and k from 2 to 246 or 46 maximum of here we can observe 8. Okay. Ah, so with varying of k and with varying of n here we can observe how low level of information consists image, how it is actually changing the shape and medium level information image, how it changing the shape and high level informative image, how it changing the shape. So with this varying of n, this low level image after reaching to a certain level, it becomes actually the saturated and but it is extended the medium level to certain extent. After that it is actually reducing or it is actually having some saturation, but there is no question of any saturation here. It goes on appearing like a straight line. in case of more or high level informative images, if varying of n as well as k. But after a particular range of varying of n means number of dots per inch. Okay, there is no much changes we can observe on high level images, but in the both the cases of low level and medium level, we can observe maximum changes of varying of n here, just this particular slope of curves. So isopreference curves tend to become more vertical as details in the image increases. This is the conclusion statement for this particular isopreference curves. This isopreference curves becomes more and more vertical as details in the image increases. Details in the image increases means high level details or appears in the images means automatically that particular curve increases or appears more vertical. That's the meaning. Then perceived quality remains the same while n increases but k decreases. But quality there is no any difference, but it remains the same while n increases but k decreases. Even though k decreases, there is no chance to have any difference on perceiving the quality of images. Okay, this is, I mean, brief introduction regarding that particular spatial and intensity resolutions. Okay, coming to the next. These are just observation of the spatial, sorry, interpolation or as well as 72 dots per inch image if you have zoomed out for the particular size 3692 to 2812 pixels using nearest neighbor interpolation. Of course, interpolation concept is not there in your syllabus, but this one showing with varying of 72 dots per pixel, and with this interpolation concept, there is a chance to reconstruct the original image with this interpolation concept from 72 dots per pixel even. What are those, just we can observe in this? Base, okay. Interpolation here, okay. Interpolation just missed this particular thing. There are three different types of interpolations. That is nearest neighborhood interpolation, as well as bilinear interpolation and bicubic interpolation. Through this interpolation concepts, we are replacing, that is, intensity level assignment for one pixel. Look for its closest pixel in the original image and assign its intensity. That is called nearest neighborhood. That indicates I can define you if you say about your friends. Some such type of sentence is there in English. In the same way, if you want to know the correct pixel values, if you identify the nearby pixel values, there is a chance to replace that pixel value also with the nearest neighbor pixels. That's a called a nearest neighbor interpolation. And based on undesirable effects such as distortions, if you observe, with the bilinear interpolation we can use here four nearest neighbors to be considered in order to interpolate